Circle geometry, tangents, part 1. We should all know, of course, that a tangent touches a circle, only intersects at one point with the circle. And there's the center O. What's the shortest distance? I think it's fairly obvious because all these other places are outside the circle, so it's fairly obvious that we have to go to the point of contact to get the shortest distance. But then I ask, well, what is the shortest distance from a point to a line? It's got to be the perpendicular, the right angle. And that gives us our first circle theorem dealing with tangents, and that is that the radius to the point of contact is perpendicular to the tangent. So if you draw from the center to the point of contact, that angle between that radius and the tangent must be 90 degrees. There's the theorem. The angle between a tangent to a circle and the radius drawn from the point of contact is a right angle, and the reference is rad tan, radius tangent. So let's take that a step further now. We have a tangent to a circle, and now I'm going to draw a chord. So there's the point of contact of the tangent, and I've drawn a chord. I could draw that chord anywhere. Now I'm drawing an angle subtended by the chord on this side. Now notice that if there is the chord, the angle subtended by the chord is the angle anywhere in this segment. That's what the arrows indicate. It's this whole segment here. As long as the angle from that chord has its point on the circumference, from just after that point around to just before that point there. Now I'm going to add in a diameter and join across there. You might say why, but I'm illustrating something here, that's why. Right, there's the diameter. Now if this is a diameter, then that is a radius, so we already know what? Radius tangent. We already know that that's a right angle. This is a diameter, so we already know something about this angle here. Remember from the earlier circle theorems that if we draw a diameter and an angle in this segment here, that segment has a special name. This being a diameter, it's a semicircle. So this is an angle in a semicircle being 90 degrees. Angle in semicircle. Finally, we have our bow tie here, which means that we have angles in same segment equal to one another. Now let's have a look what we have. We have 90 and the blue is part of it, 90 and the blue is part of it. So what's left is 90 minus blue, and what's left 90 minus blue. Which means these must be equal to one another. They're both 90 minus blue. So let's put those alone like that, and we have a situation like that. Always the case. Well, that brings us to a theorem. If a tangent is drawn to a circle and a chord is drawn from the point of contact, then the angles, we'll just say angle at the moment, between the tangent and the chord is equal to the angles in the alternate segment. The angle in the alternate segment, well, a chord makes segments. This chord, because that's the chord we're talking about, makes a segment here and it makes a segment there. And alternate means other. So if this is on this side, it must be the angle in that side of the chord where it sits on the circumference of that section of the circle, that segment. So it tells us if we go from the angle between the tangent chord to the chord and to the opposite side up to the circumference, there we are. There are the arrows indicating anywhere in that segment. Here's another case. There's an angle, there's the chord, so in the opposite segment. Opposite segment. Going from the bottom, the opposite segment's down top. Now this angle could be drawn anywhere, there, wherever, in that segment. Segment to the right. And segment above again. Here's angles in the same segment. Notice at angle in the alternate segment, I mean. Tan chord, tangent chord, alternate segment theorem, or angle in the alternate segments. Any one of those can be used as a reference. I prefer tan chord, it's shortest. So, there's the theorem. If a tangent is drawn to a circle and the chord is drawn from the point of contact, then the angles between the tangent and chord are equal to the angles in the alternate segment. So there's the tangent, there's the chord. We know that is equal to the angle in the alternate segment. Now the question is, we still haven't dealt with the fact that there's an S on that angle. Angles. Well, if you have a look, there's the angle between the tangent and chord, but if this is the chord, there's another angle there on the other side. And that means we can look anywhere in this smaller segment here to find an angle equal to that one. So there are two angles associated with each of these tangent chord combinations. And have a look, it's quite logical, huh? If you take the red and the blue here, they're supplementary angles because they're on a straight line. If you take the red and the blue here, they're supplementary angles because they're opposite angles in the cyclic quadrilateral. Here's a different angle. Have a look at this one here. This is equal to, well, there's the chord, so therefore it's going to be up here at that point there. There we are. And we have the angle on the other side, and there's the chord, so here's the segment here. There's no angle there at the moment in that segment, but we can draw one in. And there's the situation again where we've just used another chord in the same diagram with the same tangent. Now these two are tangents and they have something in common. They're both drawn from there, so we call that a common point. Now let's draw in a chord and an angle in the alternate segment. So that says those two are equal. It also says those two are equal, which means we have all three angles equal. That equals that, that equals that. Well, that means these two are equal. And we have equal angles in a triangle. And what do we know about the sides opposite the equal angles? They're equal. So that's an isosceles triangle. So that gives rise to another theorem that says tangents from a common point to a circle, so to their point of contact, are equal to one another. And it's called tangents from a common point, tans from a common PT. Here's some exercises to do. Try them yourself. Pause, try them yourself, then go through them. There are 2 pages of them. There's the second page. Right, let's go to the first page. Remember that what we do, if you saw my earlier videos, if you're trying to find angles, it's always better to start with what you're trying to find. So if I go to x, I say, well, what is x equal to? Well, it's on the circumference. There's the chord subtending it. Aha, there we are. X is 70 degrees, tan chord. There's y. What's it equal to? Well, there's the chord subtending it, and there's the angle between the tangent and chord. Y is 50, both by tan chord. Let's look at this next one. What's x equal to? Well, x is equal to z, tan chord, but we don't know z. But x is also equal to, there we are, alternate angles. So x is equal to 67 degrees. And remember, when you state the alternate angles, you must state the parallel lines. What's y equal to? Well, y is on the circumference. It must be equal to 67. There's the tangent, there's the chord, angle equal to the angle in the alternate segment. Y is 67, tan chord. Z, well, there are a couple of ways we can do that. Have a look. Z has a Z shape, so Z and Y equal, or Z is equal to X, either way. So Z is 67, we're using the fact that Y is 67, alternate angles, the Z shape. Number 3. What is x equal to? Well, x is equal to t, that's 50 degrees, because it's tangents from a common point, angles opposite equal sides. Well, we need to put tangents from a common point as part of the reason. It's no good just saying angles opposite equal sides or isosceles triangle, because we need to know why it's an isosceles triangle, why they're equal sides. What's y equal to? Oh, well, y is equal to the angle between the tangent and this chord on the other side. So there we are, there. So y is 50 degrees, tan chord. Now we've got to find z. Well, there's a diameter, so T1 must be 90. If we said what's Z equal to, I can't find Z equal to anything. So then we say, well, what does Z combine with? The only thing that I can tell, Z combines with X to give that, but I don't know that. But Z does combine with those other two angles. I know that one. So if I can find T1, I can find Z. Well, T1, it's a right angle triangle, angle and semicircle. So therefore Z is 40 degrees by angle sum triangle, 90 and 50 taken from 180. Number 4. We're trying to find x. Well, what's x equal to? X is equal to that, but I don't know that. What does x combine with? Well, it combines with these other two angles to give 180. And hang on, these are tangents from a common point. So if that's x, this is also x, and it adds with 40. So therefore I can use all those facts to find that x is 70. What's y equal to? N2. So we have to find N2 and y first. How do they combine with that one to give 180? What's that one equal to? Well, it's subtended by this chord. There's the angle between the tangent and chord. So therefore L is 70 degrees by tan chord. And therefore y is 55 degrees. 180 minus 70 gives 110 for both, and we halve. Number 5. What's x equal to? Well, x is equal to y, tangent chord, but that doesn't help me. That's the only thing. So I can't find x at the moment. What's y equal to? Well, y is equal to that one, but it combines with, we don't know anything there. But y does combine with these two angles to give 180, and I can find that one because it's equal to 64. So S1 is 64 degrees, tan chord, and therefore y is 44 degrees. Adjacent angle, straight line. All three add up to 180. Now that I know y, I can find x because that's tan chord. And knowing y, I have an isosceles triangle here by tangents from a common point, so we can find z. Y is 44, therefore that's 44, giving you 88, take from 180. Number 6. What is x equal to? Well, there's the chord making the angle with the tangent, so there's subtended or there's subtended by the chord in the alternate segment. Well, we have it already. X is 30 degrees, tan chord. What's y equal to? Well, y is equal to that one there by tan chord. I don't know it. Y is equal to that one there by tan chord. And I can find that because, have a look, we have this bow tie shape, the angles in the same segment. So, we can find B1 is 30 degrees, angles in the same segment, which means y is 30 degrees. Alternate angles, and don't forget to state the parallel lines. Number 7. What's x equal to? Well, it's equal to that angle there, but I don't know that one. What does x combine with? Well, x combines with 25 to give 110, because this is the exterior angle of the triangle. Have a look. There's the triangle, and we've produced a side. If you produce a side, you get an exterior angle, and in a triangle, it's equal to the two inside opposites. Why? Well, that and that add to give you 180. Those two and that add to give 180. So that is the same as those two. So therefore, we can find that x is 85 degrees by exterior angle triangle. What's y equal to? Oh, Pretty straightforward, hey? Angles in the same segment. What's z equal to? Well, z's equal to, there's the tangent, there's the chord, there's subtended, or there's subtended by the chord. So z is 25 degrees by tan chord. Let's have a look at the next one. What's x equal to? Well, x is equal to R2, I don't know. X is also equal to S3. And I can find S3 because this is an isosceles triangle and I know an angle. So S3 equals 50 degrees because it's tangents from a common point, makes those two equal. By angle sum triangle, they add up to 100, so therefore they're 50 each. And therefore x is 50 by tan chord. So we now know x. And we do a similar setup to find the other angles. Number 9. What's x equal to? Well, there's the tangent to this circle and there's a chord, so therefore we look opposite. Oh, x is equal to 40 by tan chord. What's y equal to? Well, y is not equal to anything. That's not a tangent, hey? So we can't say that is equal to this. Y does combine with 40 and that one to give 180. And hang on, I can find that one there, so that's the way I'm probably going to go. A1 is 70 degrees, 40, therefore 140, because they're equal 70 each. So we now have 70 there, x is 40, and that is 40. So we can find y. 30 degrees, tan chord. Not sure why we're saying tan chord, it's angle sum triangle. And there's a magical change. That's far better. Because you see, we can find that by isosceles triangle and angle sum triangle is 70. We already know that. Therefore, we can find y by angle sum triangle. So it's angle sum triangle, isosceles triangle are the two. Number 10. Now that's quite a sneaky one because you have to notice that these are tangents from a common point there. We'll assume they're tangents, otherwise it won't work. Hey, it should have said tangent. Oh, it does say tangents, that's fine. Right. Because that means that and that are equal to one another, which means you can find these two angles here. What's the use of that? Well, angle between a tangent chord is equal to the angle subtended by the chord. I was looking at S1 straight away because when I'm trying to find x, I say, well, what's x equal to? S1 or T1. And I can find either S1 or T1. So there we are. S1, 69 degrees, isosceles triangle, tangent from a common point, angle subtriangle. Which means x is 69 degrees. Now, from there, that's quite straightforward, you see, because if you have a look, we have radii there, which means that's equal to that. Or we have coming to the center and coming to the circumference. So we can either use exterior angle triangle or angle at center. And of course, that's the shorter one. Have a look again. There's the angle at center, the y, and there's the angle at the circumference, the x. And we know x, so we just double. Having a look at this next one, notice we have a radius and a tangent, which means, while we know that's 120, we know the size of this angle. 90 degrees. Why am I doing that? Well, I'm trying to find x, and I say, what's x equal to? I can't find x equal to anything. What does x combine with? It combines with this one to give you 120 degrees. So that's the way I'm going. And that gives us straight x equals 30 degrees. Now this is a diameter here, and be very aware of the diameters because then that tells us something about that angle there. is 90 degrees, angle in a semicircle. So now y combines with that angle and that angle to give you a 180. So therefore y is 60 degrees by angle some triangle. 90, 30 is 120, so there's 60 left from there. Now, if you have a look, what's z equal to? Well, z's equal to that angle there, straight off. So we can actually find z straight off because, have a look, there's the angle between the tangent chord, and there's an angle subtended by the chord on the opposite side. So z's 120 there. Or we have a cyclic quadrilateral here, and y and z are opposite in the cyclic quadrilateral, making z 120 again by doing 180 minus 60. Easier way to go. Plenty more in this series of videos, and we're going to get on to the riders quite soon, which involve all the theorems.